An interesting note that I forgot to tell you about. When we're dealing with sequences, quite frequently, the idea of figuring out a general term, an expression for AN, like we did with our series yesterday, isn't always obvious. What is your first guess as to what the next term should be? Yeah.
32.
Why?
It's like 1 times 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16.
So if I was thinking geometrically, you'd be absolutely correct. So it turns out that there are at least 3 different options for the next number. 32 is one of them, but so is 31. And the reason 31 could be next is due to a weird piece of geometry. I want you to take a circle. And I want you to put a number of points on the edge of the circle. If you put 1 point on the edge of the circle, well, you can't really go anywhere, right? From that point, you can't go anywhere, so there's 1 piece of the circle. But if you put 2 points on the circle and you connect them, then you have 2 pieces of my circle. If you put a 3rd point on there, then notice you have 4 pieces in your circle. If you add a 4th spot and connect, one, two, three, four, five, six, seven, 8. If you add a 5th spot, you'll get 16. If you add a 6th spot, you only get 31. Isn't that weird? Ready for the next freaky thing? You'll notice that I put those points at random spots around the circle. If I insist that the points be equally spaced around the circle, then I get 1 point gives me 1 piece, 2 points gives me 2 pieces, 3 points gives me 4 pieces, 4 points gives me 8 pieces, 5 points gives me 16 pieces, but 6 points only gives me 30 pieces. This is infuriating. It is quite possible that you can have sequences and thus series that look the same at the beginning and very differently at the end. Now, how did I find this? Well, there's a wonderful video by Numberphile about the cake cutting problem. But I also would recommend that you take a look at the following website. oeis.org. I kid you not, people have been looking for series long enough, they've built an encyclopedia of them. OEIS, the Online Encyclopedia of Integer Sequences. If you want to know what a sequence of numbers is received from, where did this particular set of numbers come from? So if I put in 1, 2, 4, 8, 16, and I make the next number, come on, move over, 30, well, it tells me right there, place n equally spaced points around a circle, join every pair of points by lines. This divides the circle into that many pieces. 7 points gives me 57. And then it gives me another way of coming up with these, and it gives me references to where it got these. And it's got a formula, and they give the code for that formula right here. Dear Lord, I would never have come up with that on my own. So I'm going to try and rig all of our problems, be simple ones. But I need you to be aware that there are some sequences that have very complicated formulas that we can run into. And the online encyclopedia is a worthwhile place if you're stuck. So that is the content portion of today. All of the rest of today is question and answer. What questions do you have for me on sequences and series?
$38.
11.2, 38, you said? Talk to me about the problem you're having with this.
I think that's on to the point where I think usually that's something like maybe on there possible.
Let's run with that. So root 2 to the negative k is the same as 1 over root 2 to the k. I'm good with that. Doesn't help if I'm off the bottom of the page. Wait a second. Wait a second. I had this same idea yesterday where I said the top of the fraction and the bottom of the fraction should both be to the same power, right? It would be easier to deal with it if they were both to the same power. But what's 1 raised to any power? So I could actually write this as 1 to the k over root 2 to the k, and then I have a power on top and a power on bottom, and they're the same power. So now this series becomes k equals 0 to infinity, 1 over root 2 to the k. What number is in front of that fraction? So if I think of it as a r to the k, and notice k is starting at 0, that matches one of my forms, doesn't it? Leo, question? Or were you talking about when I talk about this?
I was thinking the same way too.
Great. Wonderful. There are other options. We could rearrange this in different ways. But that one takes me most directly to something that looks geometric. And now you can tell me what happens and tell me what the result is. Because it says, determine whether the series is convergent or divergent, and if it's convergent, find the sum. So if it's divergent, all you have to say is it's divergent, walk away. But if it converges, then you need to use our sum formula to tell me what a total is. More questions? Yes, Leo.
So 11 to 44. For this one, I thought it would be best to break this up as ln of n minus ln of n plus 1.
Okay.
Then the sum 1 and that's 1 with ln of n start at ln of 1, then the ln of 2 to ln of 3 up to ln of infinity minus 1.
Oh, I don't know how to do ln of infinity. So let's do a partial sum, because it does say in the instructions here, express Sn as a telescoping sum. So rather than use infinity, let's look at a partial sum. So instead of going from 1 to infinity, let's go from 1 to capital N. And the reason I'm using capital N is because we already used little n in the formula. What is the first term in that first set of parentheses?
Minus ln of 2.
Well, but I want to write in the other one as well.
Ln of 1 minus ln of 2.
And you're right, ln of 1 is 0, so that's gone. But I don't want to simplify anything at this point. I want to see if it telescopes. What's in the next set of parentheses?
The ln of 2 minus ln of 3.
Keep going.
And ln of 3 minus ln of 4.
Now, the last one should be ln of capital N minus ln of capital N plus 1, right? And the one before that, this would be ln of n minus 1 and ln of n. Do we see the telescoping action?
I see how the ln of 2 and ln of 3 is going to cancel out.
And then the ln of 4 would cancel with the next thing, which I didn't write down. I didn't write down all the intermediate terms, but I can see the pattern happening. And so because of that pattern, I can say, oh, look, those cancel, those cancel. The only thing that survives, first one and the last one. Okay, so somewhere I need to dig through my son's toy cabinet when he was a little kid, see if I can find that little plastic telescope. Hey, this telescopes, now I know what happens to Sn, therefore I can take the limit of that, and you can tell me what happens from there. I'm not going to do that, I'll leave that part up to you. Better? Wonderful. More questions? Talk to me. Yes,
I'm just
Okay, 40, because it's made up of multiple pieces like this one is. Three over 5 to the n plus 2 over n. Here's where I get to say I'm going to do the arithmetic on sequences. Turn back one page in the textbook to page 714, and you'll see this. This result I just mentioned in passing at the end of class yesterday. I said, oh, we can add series just like adding terms. We can subtract just like subtracting terms, and we can pull out a constant. So I want to take the series in number 40 and pull it apart. We've got some addition here, so let's split this into two separate series. And now I'll use that first property that says if I have a constant, I can take it out. The 3 on top in the first series is just 3 times the whole thing, right? Let's put that in front. Same thing with the 2 in the second series. So now, what I need to know is, does this series converge? If so, give me its total. And does this series converge? If so, give me its total. If both of them converge, then this one converges. If either one of these diverges, stop, the whole thing diverges. But now, hey, these look familiar. And that's where in this chapter, I will say with 100% certainty, just like back in chapter 7, I've got to get to pattern matching. I've got to say, oh, that looks like a geometric thing. Just like I said, oh, that looks like integration by parts. That looks like partial fractions. That looks like a harmonic series. That looks like a other types of series. This one alternates. This one's, we're going to have lots more types of series because I got 7 more sections in this chapter to go. I'm going to have to categorize them by type, just like you did with intervals. You got a question?
So if they convert to different
Well, then these are two different numbers, right? Multiply by 3, multiply by 2, and add. The original one will converge to your total. If either one of them diverges, well, maybe it diverges because it goes to infinity. Infinity plus something, that's infinity. Maybe it doesn't have a limit, well, then the overall thing doesn't have a limit. I'm back in chapter 2. When I took things apart and I took limits of each piece, if one of those pieces was effed up, then the whole thing was effed up. I've seen this before, I promise. Better? Yeah. Better? Matt? Better? All right, more questions. Yes, sir. Same section? 11.3. Oh, we haven't gotten to 11. 60 which one? 62. So this is my first real problem involving a power series because there are x's in here, right? So let's think about, let me think about either 59 or 61. Which would you rather I do? Okay, so 61 asks me to look at 2 to the n over x to the n and goes from 0 to infinity. Dom, I'm going to play the same fraction trick. What do I do? Perfect. Now that's geometric, isn't it? What's the value of A? Oh, wait a second. This because it's starting at 0, my geometric stuff looks like AR to the n. Okay, so A is 1, and then the R is the 2 over x, yes? Aha. When does a geometric series converge? There was something special about geometrics. We had a property about R. Almost. It's less than 1 in absolute value. Oh, so let's take our expression for R and put it into there. Now tell me, what x's make that true? Ooh. Say again? If I put in 0.25, what do you get inside that R? Let's solve this algebraically. The absolute value of 2 is just 2. The absolute value of x has to stay there. And then I can cross multiply, right? So I know this actually only converges when you pick x's that are bigger than 2. So if I picked anything larger than 2, 2 over x would be a fraction smaller than 1. That works. If I pick 2 itself, I get 1, and it has to be strictly less than 1, so that doesn't work. If I pick a negative 2, that's negative 1, same deal. So our series converges out here. We have an interval, a region of convergence. Now, because this is over x, that's why the interval goes out, because we're dividing rather than multiplying. We will see that there are series that involve x that always end up with an interval going in. That's later. Better, Jack? Yeah. So I want to try and do the same thing in 62. Now I have to figure out, oh, well, where can I bound that to make it work right? More questions. Okay, I'm going to do something weird. Wait for the weirdness. I can actually think of this number line as adding one more point. If you think of going out to infinity, whether you go to positive infinity or negative infinity, as being the same place, I don't care whether it's a positive infinity or negative infinity, it's still infinitely far away, right? Then you can think of infinity as one number. Whether it's positive or negative, it's kind of neither, like zero, right? So let's take our number line and put the point at infinity. There's my point at infinity. So the right side of the number line is the right side of the circle. The left side of the number line is the left side of the circle. As I go away from zero, I go towards infinity, don't I? Well, then this interval really is one interval, isn't it? Isn't that sneaky? So I can think of the middle of this interval as being infinity. This is called the 1 point compactification. That's just a neat trick of thinking. There is a way to think of infinity as if it was a number. It's on a number line. The problem is that on that circle, distance behaves really weird, man. No matter how far you go up that circle, you never get to the North Pole. Again, I don't pull this out of my ass for no reason. There are a lot of interesting results in physics. In particular, if you think about like a black hole, you can actually never get to it. You keep getting closer and closer and closer to the edge of a black hole, and distance behaves weirdly around the black hole. Just like distance behaves weirdly around that point of infinity. All sorts of neat ideas and changes to distances happen when we change the rules of geometry. If you're interested in this at all, you should take Euclidean and non-Euclidean geometry next semester. The prereq is 207. Anyhow, thus endeth the diversion into weird physics. For today. Yes, sir.
For 40, I can't kind of figure out how to do the series of just 1 over n.
I'm cheating. We did that one yesterday. Yep. That's why I said you have to pattern match. I've seen that exact series before. I should look up what it does. Didn't talk about it for very long. Also on page 713. Ta-da! Yes, sir.
74 on 11.
74. Is this increasing, decreasing, or not monotonic? Is it bounded? Okay. My first reaction, write out the first 6 or 7 of these. Are they all going up? Are they all coming down? Or is it bouncing back and forth? Let's do that. Well, advantage is a sequence. I can do that on here. I don't have to do it by hand. I can do a sequence on my calculator. Oh, I need to be in sequence mode. Sequence mode. Okay, we're starting at 1. And I'm going to do parentheses 1 minus n over 2 plus n. It might make more sense to start this at 0 rather than starting it at 1. But that doesn't say, does it? So it's up to us. Do you want to start at 1 or at 0? Okay. If I start at 0, then the first thing I get when I put in 0 is 1/2. Okay. Well, now that I know that, I can start looking at the graph. Let me make this a little bigger. Oh. 1/2 negative 1/4. Oh yeah, looks like it's going down, doesn't it? I'd like to prove that. I think it's decreasing. We showed how to do that, didn't we? With a derivative. So I can calculus to prove it's decreasing. Is it bounded? What happens to that as n goes to infinity? Right, but does it go to a particular number? Does it have a limit as n goes off to infinity? If it does, what is that limit? And can we show we never go below it? Because then we'll be bounded below. So the advantage is once I have this, I'm really thinking back in chapters 2 and 3. How do I take the limit as we go off to infinity? And how do I show we're going down? I can take a derivative. But that means instead of working with my sequence version, I can work with a function like that. Better? Wonderful. Okay. Please notice, if I go back into that sequence mode and I get rid of this number that I put in as the minimum, it still graphs it. So I think in the future, let's not bother to fill that in. I think filling that in was a mistake. Let's leave it blank. Let the calculator actually do that part for me. More questions. I get all the way through the Jeopardy theme song in my head, we're done. I have no reason to leave your butts nailed to these chairs. I am more than willing to stay if you have other questions. Otherwise, I'll see you all on Monday. A wonderful weekend, everybody. Clearly, everybody's in a rush to get out of here. Dude, what did he say? No, honest. Nope. Does this look like a squid? Akbar, I am not. Hit me. Right.
Is that just because it fits that?
Well, if we look at some of the other problems that are involved in that section, in those few series, almost all of these have powers of n involved where the x's are, right? So almost all of these are geometric in some fashion. We will see there are places where, like this last one down here where it's e to the nx, that almost doesn't look like it should be geometric, but I have that trick that Jana mentioned yesterday about powers being multiplied, right? It's powers of powers. So there are ways to turn almost all of these into geometric. That's because we really haven't run into any other kinds of series except the harmonic one, right? And that's about it. We'll develop other types, but at this point, it's either geometric, telescoping, harmonic, or it's something I can figure out a pattern for, like we did over here. Yeah. Eventually, we'll have a lot more options to pick from, but right now I don't. Why we do this one early. You as well, Tom. Talk to me, Jay.
I had one and I looked at the thing to make sure it was a problem numbers, and then I looked at it and I lost it.
You'll find it in a second. Keep looking. It's okay. And we can look at it even if it isn't a problem of ours. I mean, I have no reason not to keep practicing. Sequence or series?
It's 11.
Okay. It's okay. For 30, yes. Here's my question. Either harmonic, geometric, telescoping, or somehow I can find a pattern, right? Okay. I'm pretty sure that's not geometric because there's not a K in the power. I'm pretty sure it's not harmonic because there's a square there. Harmonic has to have 1 over n. This has other stuff. 1 over k in this case, right? Maybe it's telescoping. So I say to myself, can I do partial fractions here? But when I look closely, the bottom doesn't factor. Or there's one other option, right? We said in order for this to converge, the bits have to keep getting smaller. Which means if the bits don't get smaller, it doesn't converge. And I said that was actually the important part. We called it a test for divergence. Since right now I don't think it matches any of my formulas, let me do that test real quick and see if I even need to try and find a formula or something. So let's try the test for divergence. And that means I need to take the limit as k goes to infinity of this. Here's the best part. The only thing I need to know is this limit not 0 or is it 0? If it's not 0, we diverge. If it's 0, then I gotta go back and start looking at other stuff. But if that limit is not 0, I'm done. I can walk away clear. What is that? Ta-da! Now, I would recommend that you actually tell me what the limit is rather than what it isn't. But if you know what it is, it's not 0. You're done. So I got the cheat shortcut, having try and find a pattern, having try and see the telescope, all of that by testing to see if it diverges. Hey, this does diverge. Stop. I don't have to do anything. Well, I like that test. It's really just stuff we did last semester.
Wait, now what is actually, my biggest issue with these is, which one of them it is.
Which is the same problem we had back in chapter 7, where it's like, oh, here's an integral, what the hell do I do with it? So that's really going to be, I think the best way to practice that is to look at a whole bunch of these and say, what can I try? And I think it's section 5 or 6. We'll do the same thing we did back in chapter 7. We'll go, oh, what's a strategy? What's easy versus what's hard? How should I move through from easy checks to hard checks? But it always comes down to what pattern do I recognize? And that means you got to look at a lot of these to try and find what those patterns are. I wish there was a fast, easy way for me to just upload this right into your head and I'd be done. But that hasn't worked yet. I don't have a little port in the back of my head like any of those people in the Matrix. I think I'll make a fortune selling temporary tattoos that look like USB stickers. Thunderbolt ports. Thunderbolt ports, the heavy duty ones on the big MacBooks. IEEE 1394 standard. That way I don't have to make that big thing and you don't have to shave your head, which is great. Little thumb drive sticking out the side of your neck like a Frankenstein bolt. Beelzebub, we will assimilate you.
People really like the sensation.
Sorry?
People really like the sensation.
And there you go. Have a little flash of lights. Did you know that in the Star Trek board movies, all of the lights on the boards flash in Morse code? And not only that, they spell out names of effects artists. The effects team snuck that in. Anyhow, as soon as I can figure out how to upload this, teaching will be done. You'll come to university, we'll plug you in, and we'll leave. All right. I will see you all on Monday. A wonderful weekend.